everyone. Today in this lecture we will discuss about resilient modulus of bituminous mixtures. So I will discuss about what is the modulus value that is being used in the pavement design context with respect to the AASHTO standards and as well as with respect to the IRC standards. What is the history of development of this pavement method, pavement design strategies over a period of time, but this will be in the context of use of material or the material characterization alone, and I will not be going in detail about the pavement design strategies. Okay. So we have ASTM protocols to determine the resilient modulus of bituminous mixtures. Those will be discussed in detail. So as we all know, this is a typical cross section of a bituminous pavement. We know that the bottom layers, the base, sub-base, cores and all are granular materials, whereas the top layers are the bituminous layers. Okay. So this granular material essentially shows a elastic behavior or an elastoplastic behavior, or you can say that's a plastic behavior. Okay. Whereas the top layers or your bituminous layers exhibits viscoelastic behavior. Now when you want to design a pavement layers like this, we should have sufficient information about the material behavior. You should have some modulus value which will go into the analysis of this pavement structure. Okay, let us first discuss about granular materials. The modulus value for granular materials is more or less straightforward because the understanding about granular materials is or to some extent well established, wherein we know that especially in the case of a pavement structure, the granular layers comes at the bottom. Okay. So during their construction or compaction, they will be subjected to substantial amount of loading, and hence a lot of permanent deformations or the plastic strains might have already happened in the material, and the material might have reached a steady state. So if I continuously load a material, you can say that there will be recoverable as well as irrecoverable deformations, but after a certain point of time, your irrecoverable deformations will cease and there will be only recoverable deformations. So when this pavement is laid compacted and when the load, you mean the traffic load comes on top, the amount of traffic load intensities that is distributed to the bottom granular layers will be substantially less, and also since the material is preloaded sufficiently, you can say that there will be only resilient deformations that will happen in the material. So this is what it's mentioned here. So no more permanent deformations will happen in the material. Whatever deformations that happen is resilient in nature, and one will be able to identify a modulus value based on this resilient deformation. As you can see here, this is a strain versus time plotted for a repeated loading test on a granular material. So see that, okay, these are the strains over the repeated number of cycles. Over a period of time, you can see that the accumulated plastic strain as shown here has come to more or less a constant, whereas it is the recoverable deformation or recoverable strain you can straight away measure from this, and the modulus can be explained as the ratio of the repeated stress to the recoverable axial strain. Okay. So this is the modulus, or this is called the resilient modulus, which is what is used to characterize the granular materials. Okay. So when one wanted to construct a pavement structure with bituminous layers on top, they wanted to characterize the top layers also using a similar resilient modulus procedure, so that a similar kind of test procedure can be adopted for this material as well. Okay. So let us discuss about how the AASHTO design method has evolved over a period of time, and what are the kind of moduli that they have considered during the design process. So here, as you know, this AASHTO pavement design strategy was developed as part of the AASHTO road test, which was from 1958 to 60, which collected considerable amount of information from the road data, such as the pavement surface evaluations based on roughness, deflection and the strains happening in the different layers. The pavement surface index, serviceability index are also computed. So based on all these informations, they have come up with the design strategies in which resilient modulus was chosen for flexible pavement layers, and essentially the design was based on a layer coefficient concept. So in that, the resilient modulus of bituminous material is also taken as a parameter. Okay, and essentially what you look at is how the serviceability conditions of the pavement deteriorate over a period of time, or what is the kind of deterioration that is permissible, and accordingly you will design the pavement structure. So that was the whole idea. Now in 1993 the idea of design of pavement as per AASHTO was to determine a pavement structural number that will be able to take care of the design equivalent standard axle load. So whatever traffic is coming, you decide what should be the structural number for that layers, and from the structural number you decide how much should be the thickness of each layers. Now the structural number is computed like this, which is a cumulative of the layer coefficients multiplied by the layer thickness. Say for example, you have multiple layers, granular layer and bituminous layer. For each layer you will have a layer coefficient A1, A2 and so on, and D1, D2 are the thicknesses for these layers. So sum of this will give you an indication of the structural number. Okay. So first what is decided is that for the design traffic you identify how much should be the structural number, and knowing the layer coefficients you can identify how much should be the layer thickness. So that is the whole procedure, in which the layer coefficient for the bituminous materials is defined in terms of the resilient modulus. As you can see from this chart, for estimating the layer coefficient for bituminous layers, so this is for dense graded asphalt concrete, this is given here based on the elastic modulus of this material. It is denoted as elastic modulus or resilient modulus. Based on the elastic modulus, the layer coefficients are identified. So these layer coefficients goes into the design of flexible pavement layers as per AASHTO 1993, and the resilient modulus were determined as per the D4123 protocol. Now coming to the latest mechanistic empirical approach by AASHTO, which was developed in 2002 and later revised in 2008. You call it as the MEPDG approach, or the mechanistic empirical pavement design. Here the material modulus is developed as a dynamic modulus. So dynamic modulus is something which is time dependent as well as temperature dependent. So understanding the fact that this is a viscoelastic material, and then you should capture the characteristic of the material in the time with respect to time as well as with respect to temperature. Different the modulus values will be captured at different frequencies and temperature, and then later shifted to a master curve, and that will go as an input in the design methodology. For the computation of dynamic modulus and development of master curves, everything will be discussed in some other lectures during this course itself. So MEPDG allows you to have 3 stages or 3 levels of design: level 1, level 2 and level 3. In the level 1, it is expected that you conduct laboratory investigations to determine what is the dynamic modulus value as well as the Poisson's ratio, whereas in the level 2 and level 3 you can have predictive equations. So based on the bituminous material character or bituminous material aggregate skeleton, based on the binder content, binder type that you have used, what is the viscosity of the binder and the temperature of test and everything, there are predictive equations provided to determine the dynamic modulus also. So either one can use the predictive equations, or you can do the dynamic modulus test in the laboratory to investigate these parameters. So this is noted here, the dynamic modulus either from the dynamic modulus test or using the predictive equations. And the Poisson's ratio is also either regression equations are given, or you can do it from the laboratory testing. And regarding the tensile strength, again you can do a tensile strength test, or regression equations are provided if you are working with a level 3 of the pavement design. Now coming to the Indian scenario, we have been designing pavements based on IRC 37 standards developed way back in 1970s. IRC 37 started with the design of flexible pavement layers on the basis of CBR of the subgrade, or the subgrade strength is taken as a parameter to identifying or to evaluating what should be the layer thicknesses. Okay. And it was later modified in 1984. Again, it is an extension of the CBR method itself, where the subgrade strength or CBR forms the basis for finding the layer thicknesses, and also the minimum thicknesses are specified for different types of layers. Suppose you are using a bituminous layer or the granular layer, what should be the minimum thicknesses required is also defined in IRC 37 1984. Now, the later revision of IRC in 2001 was to cater for higher traffic, say of the order of 150 million standard axles. They started using the semi-mechanistical approach, or again that can be considered as a semi-empirical approach or a semi-mechanistic approach, based on sufficient data that was collected as part of the Ministry of Road Transport and Highway project, R56 project. So, that field data was correlated to various laboratory investigations, and then this methodology was devised. So, in this, the pavement structure is considered as a 3-layer elastic system, okay, and a layer elastic analysis is done to find what are the critical stresses in this layer. Say for example, this is a subgrade, and this is a granular layer, and this is the bituminous layer. The tensile stress at the bottom of the bituminous layer is identified as epsilon T is critical as far as the fatigue behavior of the material is concerned, and the compressive stress on top of the subgrade epsilon V is considered as a critical parameter when you consider rutting, okay. And based on this field study, 2 distress transfer functions are provided. One is for the number of repetitions to failure due to fatigue, and the second one is number of repetitions to failure due to rutting, okay. And as you can see that the material parameter is estimated as a modulus of elasticity, which is given as E here, and the code also provides you indicative values, or the values that you can choose for the design of the structure. Say for example, these are the elastic modulus values given for bituminous materials, say BC and DBM with an 80-100 penetration bitumen at say 30 degrees Celsius is 1455 MPa. So, this was the elastic modulus values which are given in the design code of IRC 37 2001. Later revision in 2012 also gave a similar structure, and the approach is also same, wherein the bituminous surfacing, it is mentioned that it has to be a rut resistant mix and it has to be a fatigue resistant mix. The layer towards the top, bituminous layer towards the top of this towards the surface should be rut resistant, and the bottom bituminous layer should be fatigue resistant, and also the critical stresses that are identified are epsilon T and epsilon V itself for the fatigue and rutting distress. So, as you can see, they have used data from MORTH R6 and R19 studies, and these equations were further calibrated using data from R56. So, you have 2 expressions given for rutting and fatigue. One is at 80% reliability level and the second one is 90% reliability level. So, these are the 2 expressions related to fatigue behavior, and these are the 2 expressions related to rutting. Again, this is at 80% reliability level and this one is at 90% reliability level, okay. So, as you can see, there is an MR is a coefficient that goes in here, which is the resilient modulus, okay. So, as suggested by IRC 37 2012, these are the resilient modulus given, values given for different bituminous mixtures, and the test protocol they have used is ASTM D7369 Note 9 by indirect tensile strength test, or ASTM D7460 wherein a fatigue failure test by repeated flexural bending test is conducted. So, these are the values that are given in IRC 37 2012 for different types of mixes and for different types of binders. Now, coming to the latest edition of IRC 37, which is IRC 37 2018, a similar approach is adopted here also. The layers are analyzed as linearized elastic layers, and then the rutting and fatigue transfer functions or the distress transfer functions are derived based on the MORTH data itself. But there are certain modifications done on the equations. So, as you can see, the first 2 expressions are for fatigue failure. This is at 80% reliability level and this is at 90% reliability level, and this is for rutting at 80% reliability level and this is at 90%. There are certain modifications done here. For example, a parameter C is introduced with an M constant so as to introduce the variations that may come in the aggregate structure. Say for example, what is the voids filled with bitumen, what is the voids in mineral aggregate and so on. So, those parameters are also incorporated in the distress transfer function. When I say failure, NF represents what is the number of equivalent standard axle repetitions for failure due to fatigue, and when I say failure, it is 20% of area is cracked, is termed as failure. Whereas in rutting, N corresponds to number of repetitions of equivalent standard axles for failure due to rutting, and a 20 mm deformation on the surface is noted as rutting failure. So, here MRM is the material modulus that is given here, which again is a resilient modulus. So, IRC 37/2018 gives indicative values of resilient modulus for the various mixes and binders. Say for example, for the first mix BC and DBM with VG10 binder, for different temperatures start from 20 to 40 degrees, these are values given in EMPA, these are the modulus values, and these values are estimated using as per ASTM D4123. Now, there is an it is also specified that one can always use these values for the design of the flexible pavement, whereas if you want to investigate the resilient modulus for other materials using say modified binders, you can estimate the values at 35 degrees Celsius using the same ASTM standards, but this ASTM standard is now withdrawn and it has been replaced with a newer version, the latest version, but the code specifies that you still use this ASTM 4123 standard at 35 degrees Celsius, and in the standard you actually assume a Poisson's ratio of 0.35. We will not compute what is the vertical deformations. So, you have to do it as per the old standard itself and for a DBM mixture, and if it is found that this value is higher than what is specified in this table, one has to go and use what is provided in this table 9.2, that is indicated as the maximum values. Okay. So, this is what is mentioned in IRC 2018. So, we have an earlier version of the code which is ASTM D4123, which is to be used as per this IRC method, and also a later version of ASTM code for the determination of resilient modulus. So, in the coming session we will be discussing about both these code practices. IRC also give you some empirical relations to determine the resilient modulus in terms of the indirect tensile strength of the material. Say for example, on a 150 mm diameter sample for DBM specimen at 35 degrees Celsius, the relation of resilient modulus with the indirect tensile strength value is denoted here, and also for a 102 mm diameter specimen with polymer modified binder with elastomer as the modifier at 35 degrees Celsius is also given here. So, you can do an ITS test on this specimen and appropriately substitute in this equation and to get the resilient modulus value. So, these are some empirical relations also provided in the code. Let us discuss about these two standards. One is the earlier version of ASTM standard for determining the resilient modulus, and one is the latest version, and how this test is conducted and what are the post-processing methods adopted we will be discussing in the coming slides. So, let us look at ASTM D4123, which is the 1995 version of ASTM. Here a specimen, a cylindrical specimen will be subjected to a loading in the diametral direction, and then a repeated compressive Haversine load will be applied, and you will denote what is the deformations that is happening. This is what we are capturing. Okay. So, this is a typical sample that is shown here of diameter D, and it is loaded in the diametral axis. So, this is a loading membrane. Through the loading membrane you apply a load of P. Okay. Now, the specimen diameters dimensions are you can do it on a smaller size specimen or a larger size specimen of 102 or 152 mm. If your nominal maximum aggregate size is still 25 you go for a 102 mm size specimen, and if it is more than 25 and less than 38 mm, you go for a 152 mm size specimen, and the thickness of the specimen or the height of the specimen is 50 mm and 76 mm respectively, and you provide the loading strip on top on the specimen. You provide the loading strip which should have a width of say 13 mm or 19 mm. So, this is how the loading is done. The first figure shows the load time pulse. You can see that there is a loading in a Haversine fashion, and then you give a rest period. Okay. So, A is the loading time and B is the rest period and C is the total cycle time. Okay. So, such repeated load cycles will be given and you will capture the corresponding deformation. Now, the deformations will be measured in the cylindrical specimen. You will measure the deformation in the horizontal direction as well as in the vertical direction. You can use linear variable differential transducers to measure these deformations, but this code says that you need not collect the vertical deformations, you can collect only the horizontal deformation also. But if you are not collecting the vertical deformation, then in that case you have to assume the Poisson's ratio for the computations. Okay. So, the first figure, as I said, shows the load versus time, and in the second figure you can see that as the loading increases, your deformation increases, and when it is unloaded, the deformation decreases, and during the rest period also there will be recovery of deformation. So, you see a recovery of deformation here. Okay. This continues, and what we are looking at is there is certain amount of instantaneous recovery that happens. So, when one starts unloading, there will be instantaneously there will be a recovery, and during the rest period there will be a continued recovery. Okay. So, one will look at the instantaneous recovery as well as the total recovery that is happening in every load cycle. Okay. So, using those two recovery parts or the deformations, we will be computing the Poisson's ratio for the material as well as the resilient modulus. Okay. So, this figure shows the horizontal deformation. Similarly, you can get the vertical deformations if you connect a LVDT in the vertical direction. There also, as the load increases, your deformation increases, and as the load is unloaded, there will be recovery, and during the rest period of load also there will be recovery that is happening. Now, the test parameters are like this. You have to apply preconditioned cycle. Essentially, our idea is that you do a repeated load on the specimen so that your strain reaches a stable state, or it is mentioned here that the resilient deformation is stable. So, if I plot the deformation, you can see that this goes like this, and eventually a state will be reached when this reaches a stable state. Okay. It is not very clear whether you are looking at a stable strain or you are looking at a stable strain rate. Okay. So, what is mentioned is that you are looking for a resilient deformation. Whenever the resilient deformation becomes stable, you can do the test for the computation. So, it is mentioned that 50 to 200 test cycles are to be given for preconditioning. Now, the test temperature as specified is that you can do it at 3 possible temperatures. One is 5, 25 and 40 degrees Celsius. And at every test temperature, you can either do it at one frequency or different frequencies can be tried out. For example, you can have load frequency of 0.33, 0.5 or 1 Hertz. Now, as I said, it is a load Haversine wave with a rest period. Now, this load duration can be 0.1 to 0.4 seconds. This is what it is mentioned in the code, and it is ideal to choose 0.1 second in order to consider the traffic loading. That is what is mentioned. So, essentially you go for a 0.1 second loading, and the rest period also, suppose you want the cycle to be of 1 Hertz frequency, you can have 0.9 seconds of rest period. So, your cycle will look like 0.1 second loading and 0.9 seconds of rest period. So, it is a 1 Hertz cycle. Similarly, you can go for 0.3 Hertz or 0.5 Hertz as suggested by the code. And what should be the maximum load? So, you said there is a peak load. So, what should be this P max? Okay. This P max has to be 10 to 50% of the tensile strength. So, what you have to do is that for the test condition, say for the particular temperature and frequency of testing, for the particular mix that you are looking at, you have to cast specimen and test it for the indirect tensile strength and find out how much is the indirect tensile strength of the maximum load in the test, and then 10 to 50% of that can be applied as the maximum load in this test. Or you should go for say 4 to 35 Newton per millimeter of the specimen thickness is the maximum load that you can apply. That is what is specified. Now the conditioning is that at every temperature you are testing, you should condition the sample for sufficient long time, and if you are not, you can monitor the temperature of the specimen, and if you are not monitoring, you should at least condition for 24 hours. And also one more thing is that you look for the cumulative deformations in the material. If you see that this cumulative deformation that is happening is more than 0.025 mm, then you can assume that the material is going to be a failure stage or going somewhere towards a failure stage. So the code says that if it goes beyond 0.025 mm, you have to bring down the parameters, say you have to reduce the load or you have to test it at a lower temperature. Okay, so you are not allowed to exceed this 0.025 mm limit of total deformation. Now regarding the fixing of LVDTs, the gauge length for an LVDT suggested here is the full diameter of the specimen. As you see here, this is your specimen and this is the diameter of the specimen. You connect an LVDT to capture the deformation of the full diameter of the specimen. Okay. Now, as you see here, this is the horizontal direction in which you will collect the deformation, and also as mentioned you can have the vertical deformation also, or you can you don't have to do it if you are assuming a Poisson's ratio. So if I connect it like this, I have two LVDTs, one in the horizontal position and second one is in the vertical position. Okay. Now you do the test at this position, this is the first position, or I call it as a 0 degree position, and after the test is completed, immediately you will turn the specimen by 90 degree so that your this becomes your 1 and this becomes your 2. Okay. So you will just turn it and then repeat the test. So this is essentially to eliminate if there is any variability in the measurements in the vertical and horizontal direction. So that is why you do it in both directions. Okay. So you call it as a 0 degree position and the other one is called the 90 degree position. Okay. And always you test at least 3 specimens to check the repeatability of results. Again, the test can be conducted at a particular temperature. For the 3 specimens, you can go for 3 different load durations as well as the frequencies. Now, for every test, you measure the recoverable horizontal and vertical deformation. Suppose you have both LVDTs connected over the last 3 loading cycles after the preconditioning cycles. As I said, 50 to 200 cycles of preconditioning has to be given till your resilient deformation becomes stable, and after that you take 3 cycles. Those 3 cycles will be used for the computation of the resilient modulus. Okay. Now, as I said, vertical deformation can be omitted if Poisson's ratio is assumed. Okay. Now, these are the computations. So, from the last 3 test cycles, you take the average value. So, suppose this is the deformation. It goes down like this. Okay. So this is a deformation of one cycle I have noted here, either so I will just mark it as delta or delta, sorry, and this is time. First of all, you have to note how much is the instantaneous deformation. Okay. As I said, during the recovery, so suppose this was your 0.1 loading cycle. So when you have load is unloaded, instantaneously there could be certain amount of deformation. So that deformation will be marked as delta instantaneous, delta I. Suppose I am looking at the horizontal LVDT, I will mark it as delta HI, and when you are looking at the vertical LVDT, you mark it as delta VI. So I is denoted for the instantaneous recovery, and the second one is the total recovery. So from the maximum point till the end of the test, you see that this much of deformation is recovered. So if I mark it as delta T for total, this is a total deformation. So if I look at the horizontal LVDT, I will mark it as delta HT, and if it is a vertical LVDT, it will be marked at delta VT. Okay. Now based on the horizontal deformation and the vertical deformation, you can compute the Poisson's ratio using this expression. You have certain constants here related to the gauge length and its arrangement. So this is the expression for finding the instantaneous recoverable Poisson's ratio. So, it is noted as nu Ri. I stands for the instantaneous part and R is called the resilient. Okay. So, nu Ri corresponds to the instantaneous resilient Poisson ratio, which is computed using this expression. Now, as I said, you can note the total recovery also. So, based on the total recovery, you can get a Poisson's ratio which is termed as a total resilient Poisson's ratio nu RT. So, once you get your nu Ri and nu RT, you can get two resilient modulus values. One is the instantaneous resilient modulus and the other one is the total resilient modulus. So, this is the instantaneous resilient modulus of elasticity given by the equation as shown here, where P is the load that you have applied in newtons, nu Ri is the instantaneous resilient Poisson's ratio, T is the sample thickness as you see. Okay. This is your sample. So, this is T and delta Hi is the instantaneous recovery in the horizontal direction. Similarly, you can compute the resilient modulus as per the total recovery. So, ERT represents the total resilient modulus of elasticity, which is connected as here load nu in the with respect to the total recovery, and delta HT is the total recovery in the horizontal direction. So, what you have arrived at is two resilient modulus values. One is with respect to the instantaneous recovery and the second is with respect to the total recovery. Okay, and you have two Poisson's ratio values. So, this is how the resilient modulus is computed, and you are asked to average out the values at every temperature. Suppose you are doing it for 3 different specimens, you have to average out the values and you get two resilient modulus values. And suppose you are not taking a measurement in the vertical direction, you can assume a Poisson's ratio of 0.35 for the mixtures at 25 degrees Celsius test. Now, what are the issues associated with it? The first thing is regarding the gauge length of the LVDT. As I said, you will use the entire diameter as the gauge length. So, what you are measuring is the deformation with respect to the diameter of the specimen. There could always be certain repeatability issues because there could be end effect also. Another important thing is that even if you go for say the load as 10 to 50% of indirect tensile strength ratio, indirect tensile strength, the deformations could be very large. Okay. So, it can so happen that your total deformation limit of 0.025 may get exceeded. Okay. The aspect is, suppose you go for a shorter gauge length. Okay. Then the advantage is that your repeatability will be more because these end effects will not be much there, and also you will have much more control in the test. And another aspect is that you can have a larger loads may not cause excessive deformations. Okay. So, it is not sure whether using a total gauge length or a gauge length for the diameter is a better choice or not. And the another one is that it is mentioned that you have to attain a stable stage in this strain. So, as I said, it is not clear whether this 200 cycles or 50 to 200 cycles of preconditioning will help you to attain that strain of a constant strain, or it could be a constant strain rate also. That also is not clear. Okay. And again, you have to check whether the material has reached its failure state or not, because you do this preconditioning cycles. Say for example, if you are taking 50% of ITS as the load and you choose certain frequency and do the testing, and at the end of the test your specimen might have failed. So, it is necessary that you conduct an ITS on the specimen after the testing and check whether there is much variation from the results and your material is failed or not. So, it is essential to note whether this test sequence that is given will be creating a deformation in the resilient elastic state, because that is what we are looking at. Okay. And the selection next is the selection of load and the load pulse. As is mentioned, this 10 to 50%, will it be sufficient to create sufficient deformation, or will it create more deformation than it is required, is one thing. And the another thing is the duration of the load pulse. As it mentioned, you can go from 0.1 to 0.4 seconds. So, what exactly one should take is not clear. So, regarding the load pulse, its duration, then the preconditioning cycles, and also the gauge length that you have to choose, there is a little bit of uncertainty or confusions in the selection of all these parameters as far as this AS4123 is concerned. Okay. Now, many of these issues are addressed in the latest revision, which is ASTM D7369 11.